steady state error with respect to a unit step reference input was obtained as 1 divided by 1 plus k. Okay, so we saw that only for a type 1 and a higher system, we could have zero steady state error, right? Because for a type 0 system, the value of KPE was the open loop gain K0, KO, and we can assure, like a zero steady state error when tracking a constant step input, right? Only if we had a type 1 system or higher. Okay, so that is very important. Consequently, we observe that we had we observe the importance of having an integral term because the integral term 1 by s, right, helps us achieve zero steady state error while tracking a constant reference input. Okay, so that's where we stopped last class. So now let's continue with our analysis of steady state performance. So the next input we shall consider, what happened here? Yeah, the next input that we shall consider is a unit ramp reference input. As we know, unit ramp is R of t is t. Why do we consider all these things? Like let's say let's say we see some reference trajectories in automotive applications. Suppose, let us say we want to follow some velocity profile, right? So it may increase with time and then like settle down, it may decrease and so on, right? So there is nothing like an instantaneous signal or an instantaneous output. So it is a combination of ramp and constant signals and so on. Sometimes we may have parabolic signals also, like we may want speed to increase like this and decrease like this. So that is why we are considering all these type of standard signals, right, in multiple applications. So if we want to track a ramp input, R of t becomes equal to t, then R of s becomes equal to 1 by s squared. So if you look at the steady state error ESS, if we substitute 1 by s squared for R of s, we come to this expression, okay, limit s tending to 0, 1 by g of s h of s, okay. So now we define what is called the static velocity error constant, KVE, which is defined as the limit s tending to 0, s times g of s h of s. Okay.
Sir, sorry to interrupt.
Any questions? Please go ahead.
Sir, that before term should have been s into g of s into h of s, right?
Which one? Yes. Sorry. Yeah, this should be, there is a typo here. Thank you. No, so this is s into g of s. Yeah, thanks for that.
Okay.
Yeah, that's right. So KVE, in fact, is defined as limit s tending to 0, s times g of s h of s. So the steady state error when we are trying to track a ramp input is 1 by KVE, okay, as per this expression. Now, if we construct a table and we look at the value of n, capital N, right, in the type N system, and then like we tabulate the value of KVE and the steady state error. Yeah, any other questions or points? So if we tabulate the error values of KVE and steady state error, what happens is that like for a type N system, type 0 system, KVE becomes 0, because if we recall, this is the definition of, or the canonical form, right, for the open loop transfer function that we are considering in this discussion. So we have s power n, TAS all the way till TPS plus 1. Okay, so if we have capital N to be 0, immediately there is no s term in the denominator. So when I multiply g of s h of s by s and take the limit s tending to 0, KVE becomes 0. Then the steady state error for a ramp keeps on increasing. That's what this physically means. Like what it means, it's tending to infinity, is that like like you and I are not able to track, tracking a ramp reference signal with a type 0 system. Okay, so that is the implication. Now, if you have a type 1 system, what happens? N becomes 1. There is a 1 by S term, right? So then when I multiply by S, that S and S cancels off, then we are left with only K naught when we take the limit S tending to 0. I hope that is clear, right? So when we have one system, capital N be 1, KV becomes K naught, and the error to track, steady state error while tracking a ramp input becomes 1 by K naught. So in other words, the steady state error is a reciprocal of the open loop gain. Okay. So obviously, just like what we observed with unit step tracking with the type 0 system, with a type 1 system and a unit ramp input, if we make the open loop gain as high as possible, the steady state error will reduce in magnitude. However, that is not a feasible solution, right? Because a high open loop gain has some other implications. Okay. Consequently, this is what we have. But if we go for type 2 systems and higher, so if you have n equals capital N equals 2, we have a 1 by S square term in the denominator. That's what we have represented here. The S and the one of the S in the S square term cancel off. So KVE will tend to infinity. Okay, so that's what will happen. So we take the limit S tending to 0, S times Z of S, H of S, the static velocity error constant will tend to infinity. Then we have the steady state due to ramp input tending to 0. Or in other words, now, if you and I want to guarantee 0 steady state error while tracking a ramp input, we want a type 2 system at the minimum, right? We want type 2 system. Or, however, like as we discussed last class, and we will be observing or we will be interpreting this as we go forward. The more the open loop zeros you and I add at the origin, the more complicated it is going to become to control or even to stabilize the closed loop system as we proceed with control design. Okay, so that is an issue with adding more and more open loop zeros at the origin, or in other words, we go for a higher value of capital N. Okay? So that is as far as tracking unit ramp reference input is concerned. As we told, sometimes we may want a parabolic profile also. Okay, so suppose if you wanted one, right? So what happens if you and I want to track a unit parabolic reference input? R of t becomes t squared by 2. R of s then becomes 1 by s cubed. Okay, that's the Laplace of t squared by 2. We repeat the same process. We essentially get the steady state error E of s to be ESS to be limit s tending to 0, s times R of s divided by 1 plus G of s, H of s. We substitute R of s to be 1 by s cube. If we simplify this, you and I will get limit s tending to 0, 1 by s squared G of s, H of s. Now, this is limit s tending 0, s squared G of s, H of s is what is called as static acceleration error constant. So, in other words, the steady state error to a parabolic input is 1 divided by K. K is the static acceleration error constant. So now, if we tabulate the value of capital N, K, and the steady state parabolic error, or the steady state error to a parabolic input, when we go for type 0 and 1, you and I will have 0 for K, because there is a s squared term here, right, in the definition of K. Okay, so we'll be still left with either a s squared term in a type 0 system or a s term in the type 1 system. So the value of K is 0. So consequently, the error will blow off, right? So it will blow off to a very high value if you and I want to track a parabolic input. However, if you go to a type 2 system, K becomes equal to K naught. Why? Because 1 by S squared will cancel off with S squared in the denominator. for a type 2 system, and consequently the steady state error to a parabolic input will become 1 by k naught. So same, what I say, interpretation. If you and I want lower steady state tracking error with a parabolic input, we want to increase the open loop gain. Okay, so we need a type 2 system and high values of open loop gain to reduce the steady state error. Okay, while we track parabolic reflex. But then if we go for type 3 and more, immediately we can see that the value of Ka will tend to infinity, and the steady state error will go to 0. Okay, so this is what we can observe from this expression. So the point is, the interpretation is, we need type 3 or higher system to assure 0 steady state error while tracking a unit parabolic reference input. Okay, but that is once again an issue, right? Because as we discussed, the more the value of capital N, the higher will be the number of open loop zeros or open loop poles with origin. As I told, we will learn that that's going to create challenges for us to even stabilize the closed loop system when we design controllers. So now, the point is, what do we do in practice, right? So, because of course, this is all theory, right? As I told, by and large, maximum we go for a type 1 system with an integral controller, right? If the plant and the feedback path do not have an integral term, right? By and large, I won't say maximum, by and large, right? Why? Because, see, as we discussed, this ramp and parabolic profiles are not going to be there throughout. Okay, it's just that, like maybe during some transient behavior, you and I, we essentially have this ramp input. Okay, so so consequently we have this ramp input, would say, only for a small amount of time, or this parabolic input also only for a small amount of time, right? So it's okay, it's okay to have non-zero steady state error theoretically, because you and I don't need to track it all the time. Okay, so that is why in practice, if you observe, by and large, people will go for a single integral. Okay, in the open loop transfer function. Even with that, we will observe that tracking or making the closed loop system stable is a task. Okay, so I would say very challenging. But as we keep on increasing the number of open loop poles with origin by making the value of capital N higher and higher, I think even to stabilize the closed loop system becomes challenging. Please remember, one of the premises for all this performance analysis is that the closed loop system should be stable, right? Only when closed loop system is stable, you and I can talk about performance. Okay? Otherwise, there is no point in talking about performance of the closed loop system without assuring its stability. Okay. So once again, in performance, we have already looked at transient performance. We looked at time constant, rise time, peak overshoot, and so on, right? So here we have looked at steady state performance, right? So I hope this is clear. All right. So any questions before we move to the next topic in this lecture on steady state error analysis?
Sir, am I audible?
Yes, please go ahead.
I'm sorry to ask this again, but can you summarize the last few points you told again, like in terms of why we are going for a n less than, typically n equal to 1 kind of inputs?
So see, there is a trade-off, right? So see, if we increase n, right, we assure 0 steady state error for more class of reference inputs, right? Steady state error for a larger set of R of t, right? Starting with step, ramp, parabolic, and so on, right? But if I increase the number of n, the flip side is in number of open loop poles also increases. Open loop poles at s equals 0. Okay, z equals 0 also increases. So that is a trade-off. Now, the point frame is that so if you and I want to track a real in actual life, okay, by and large, see, let's say we want to track the speed of a car, right? What's going to happen? We accelerate from rest, we may go like a ramp or a parabola to a final speed and keep it constant there for a reasonable amount of time. But the acceleration phase is only a finite phase, right? So you and I are not really looking at zero steady state error for a ramp or a parabola from a practical perspective, right? I'm just giving an intuitive answer, okay? So from a practitioner perspective, okay? So by and large, we want to keep, most likely we want to keep some variable constant, for extended period of time. So that is why guaranteeing a type 1 system is by and large sufficient. That is why I'm using all these terms very, very carefully. I'm saying typically, by and large, from a practitioner's perspective. See, we have looked at theory. Theory is what it is. Okay. Suppose if you come and tell me, hey, an application requires zero steady state error for parabolic reference input, I need to go with a type 2 system at a minimum. Okay. So there is no other, way or alternative. Okay, from that. So essentially, what happens is that in that scenario, I need to make things work. Okay, so there is no alternative way. Okay, so the point is, depends on our practical requirement. Okay, so if we need to ensure that we want zero steady state tracking error for more complex signals. In some special cases, we go for a higher type system. Okay, but by and large, experience has shown that using one integral in the open loop transfer function is typically sufficient. Okay, that is why we tend for one integral. I hope that broadly answers your answers and summarizes what I mean.
Very clear, sir. Thank you.
So any other questions on steady state error analysis before we go to root locus? All right. Okay. So please note the root locus file is steps PDF file is given in the same folder as video. I hope all of you were able to access it. If not, if there is any difficulty, kindly let me know. In that same folder as in videos, there is a PDF file called root locus construction.pdf, right? I hope that is visible and accessible, right?
Yes, sir. Yes, sir. We received it.
Yeah. Please go through that file today. Okay. I think this is the correct time to start going through that file. I will explain what root locus is, and then we will start going through the steps from the next class. Okay.
So sorry to interrupt again. Just another question on the previous slide. You mentioned that we are sticking to mostly Kp and Ki, but what happens if Kd also comes, because the derivative also is coming into picture, right?
Yeah, derivative is not going to impact the type N system, right? Is it not? Right? See, because even if you have PID, so the point frame is that let's say you have Kp plus KIS, right? If you have KDS, right? What we will have is that, of course, the controller transfer function will not be proper. That's okay, right? But this will become part of the open loop transfer function, right? So, which is C of S times P of S times H of S. So, when you plug this one in, you still have the type value of capital N only dictated by the integral controller. I hope that's
understood. Yeah. Sorry.
No problem. Okay. So, coming to root locus, so what is this notion of root locus? So, in root locus, what we do is the following. So, this is the standard feedback diagram, right? That you and I are aware of, right? So, the negative feedback. Okay. So, G of S is C of S, P of S. And by now we know that the closed loop transfer function is 1 G of S divided by 1 plus G of S H of S. Now, let's say we take G of S H of S to be another canonical form. Please note the difference between the previous form and this form now. Okay, so what is the difference between this form and the previous form? No. When we did steady state error analysis, so previously all constant terms were one, right, in the numerator and the denominator. Now it is no longer so. Okay, so we have factorized them into the open loop poles and open loop zeros. Okay, so that is the important difference here. So capital K is no longer the open loop gain. Okay, so we consider that we are able to write the open loop transfer function in this form, which we typically can do. Okay, so once you and I are able to write it in this form, what happens? Let's say G of S H of S written as K times S plus Z1 all the way till S plus Zn divided by S plus P1 all the way till S plus Pn, and K is a real number. Okay, so as we know, the roots of the numerator polynomial are the zeros. The roots of the denominator polynomial are the open loop poles, right? So the open loop zeros are going to be minus Z1 through minus Zn. The open loop poles are going to be minus P1 through minus Pn. Okay, so that's what we are going to have. Now, the question is the following. Okay, so if you and I have a visual tool through which we can observe how the closed loop poles change as the parameter K is varied. Okay, it will be very, very useful. Why? Because if you remember, we did one example, right, or exercise where we took the S plane and we had sort of like an open trapezoid region for performance, right? So suppose, let's say somebody tells us, okay, you have these two as the trace of the closed loop poles as you vary K. Okay, so then you see that this is K1. At this point, this is K2. We observe that when K is between K2 and K1, okay, both closed loop poles are going to be within that open trapezoid region, right? And that is the region which I want for both closed loop stability and closed loop performance. Suppose if such a tool existed, right? Suppose if such a mechanism existed, right? It is very useful for you and me. Why? Because as we, what to say, learned, even if we were to design a proportional controller, right? You and I go from minus infinity to plus infinity. Okay. So what happens is that like it's an infinite range, right? From stability, let's say we gain a finite, not a finite region, but a smaller infinite region. But from this root locus analysis, right? If you and I are able to say, okay, look, you know what? If I vary my K between K1 and K2, I can ensure both stability and performance, right? And that is the advantage we get from root locus. That is, we are able to get a graphical representation of the trace or the locus of the closed loop poles as a system parameter is varying. That's why it's called root locus. So we will be looking at root locus for the next few lectures because it's a very, very important design tool. Okay. Of course, today in MATLAB, if you use a command R locus, you will almost instantaneously get the root locus. But the point is, yes, we do have software for all those things. It's a convenience, but you and I still need to understand the physics, right? So that we gain an insight into the overall process, and we are also able to do proper design, okay, of the controller, right? As the case may be. Okay, so this is very important, and that's why it's called as a root locus. So all of us know what the meaning of the word locus is, right? Locus means it is a trace of something, right? As we vary some parameter. What is this root in root locus? Root in root locus means it is the locus of the roots of the closed loop characteristic polynomial, which is 1 plus g of s. Because as we know, the closed loop poles are the solution of the equation 1 plus g of s h of s equal to 0. Okay. So the solution of this equation are the closed loop codes. So consequently, we are interested in the roots of this equation. Okay. So root locus is a graphical tool which tells us how the roots of this particular equation will vary as we vary a system parameter. All right. Okay. Fine. I hope the notion of root locus is clear. All right. Any questions on what is the definition of root locus? We are going to learn what is root locus or how do we construct it, right? But any question on the definition? No. Yes, please. Any questions?
If you have to applicate in terms of ride and handling, just to have a physical connotation, how do we applicate the root locus principle?
Can you repeat the question? I could not.
Sir, just of Keshav, I'm just repeating it. So just to get some physical connotation with vehicle dynamics, can you just give an example for the root locus?
Yeah. So essentially, many times, for example, if you want to, control the speed of a motor, right? You want to design a controller which will, regulate the voltage input, so that like you get a corresponding speed output, right? You can get the system transfer function, you can design controllers, and then you can use the root locus to, find out a finite range of controller parameters which will do the job. Okay. So in your projects, you will do such exercise. Okay. So even in the case of, let's say, brake control and also steering control and so on, you will use root locus to figure out what will be the range of these control parameters that will which will satisfy both closed loop stability and closed loop performance. Okay, and you will be able to get a finite range, which you can then take it to the actual vehicle and find it. Okay, so we will be doing it as part of the projects. Okay, so but first we will learn how to construct the root locus. Although in your project you will use the R locus command to easily construct the root locus, but as I keep on telling, see, as engineers, we need to know the physics and the intuition behind all these tools, right? So that only then tomorrow, if somebody gives us this data in practice, we need to look at it and interpret it, right? For that, we need to know all this theory. Okay, so that's what we are. Fine.
Okay,
So yeah, so the main practical advantage you and I will get is that, see, we initially start off even with the proportional control, right? We initially start off with a range of minus infinity to plus infinity, let's say, to begin with, right? Then let's say by using stability, let's say we go from, I'm just taking 1 to infinity, okay? So let's say we have such a situation. Then by using root locus, we say we go to 5 to 20. This K1 is 5 and K2 is, let's say, 20, right? Then what happens is that, we have progressively improved things, right? Because, we started from minus infinity plus infinity, and then we have come to a very finite range. Okay, and that is the advantage you and I will get. Okay, so I hope it's clear, right?
Yes, sir.
Okay. So anyway, we are going to look at the root locus steps from the next class. Okay, so we will get started with that in the next class, because I don't want to start the next lecture today. Then we will end up in somewhere middle, and then we need to restart again. But then please go through that PDF file, and then we will discuss it in the next class. And the one thing, unfortunately, due to some unforeseen things, I will not be able to take tomorrow's class. So next we will meet on Wednesday. Okay.
Okay.
Tomorrow we will not have a class. Sorry about that. Right?
No problem.
So any questions on the material that we learned today, or any other questions? So yeah, let's look at also attendance today. Arunachalam, is everyone present today? No, so
Yes, sir. Mostly, sir. Yes, sir.
okay. So yeah, then I will mark attendance for everyone.
Right, sir.
Yeah, please remember the date for our midterm. I think we agreed upon March,
9th,
right?
9th,
Yeah. So we will agree upon the syllabus for the midterm later on. Okay.
Right, right.
All right. Okay.
So one more also, sir. As you allow one pager formula sheet this time also, sir.
Okay, you want to bring one page formula? No problem. Okay, one A4 size. You can bring one side of it. Okay. Yeah.
Right, sir.
Sure. No problem.
Thank you, sir.
All right. Okay. Yeah. Any other questions? No. Okay. So if not, maybe we can close today's session. What we will do is that once again, we will not have a class tomorrow. We will meet on
Wednesday, sir.
Wednesday. Okay. All
Right,
right.
sir.
Okay. Thank you all. Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Good day.